Welcome to the Pre-Calculus Notes for Essential Skill B3, Part 2, Interval Notation and Inequalities. In this set of notes, our main goal is going to be to solve inequalities with a method very similar to what we used last class for sketching polynomials. First, we're going to look at a way of expressing the solutions to these inequalities. This is something called interval notation. Interval notation is a form of set notation that represents all values between a and b, for example. You'll notice that we have two different symbols. We have square brackets and round brackets. This represents inclusions and exclusions, respectively. Let's look at this example. If we have points a and b on a number line, and we want to represent all values from a to b inclusive, this is how we draw it. Close dot at a, close dot at b, and highlight everything in between. Algebraically, we represent this by saying that x is between a and b. The idea that a and b are included is reflected in the square brackets. We contrast this with the round brackets, which will be exclusive. We represent this on a number line by using open circles at a and b. And all points in between. Algebraically, we just use the strict inequality symbols. If we want to include a but exclude b, we can use a combination of square and rounded brackets. Predictably, this is how it looks algebraically. A is less than or equal to x, which is less than b. Next, we look at what happens when we have only one boundary. When x is greater than or equal to a, we represent that on a number line by extending the shading all the way to the end. In interval notation, we use an infinity symbol to represent the right end of this. We include a, and we exclude infinity, because infinity is not a number. We can never get there because it is not a number. The next one, we look at when x is less than b. On a number line, we just use an open circle, and we shade all the way to the left. In interval notation, we are required to write from left to right. Our left bound is going to be negative infinity, so we need to start with that. When we say left to right, we are referring to left and right on a standard number line. Try the next two on your own. Here are my answers. Our last three examples make use of the union operator. This is an operation between sets. Remember that interval notation is a form of set notation. So union means we have two different regions on the number line. So in the first example, not only do we have the interval from negative infinity to 4, we also have the interval from 5 to 7. Recall that the algebraic equivalent is simply using the word or. One special case we have is when we bracket only one number. This represents a single closed point, isolated. Here's what this looks like. Check yourself. See if you can figure out the algebraic way to write this, as well as the number line and algebraic representations of the last example. Here are the answers. Notice that there are two good ways to express the bottom example algebraically. Now we can look at higher order inequalities. I wrote positive negative here because all of our examples are going to be testing whether a function or a polynomial's output is positive or negative. In example 1, we're looking at where it's positive, for instance. To do this, we're going to use number line analysis. It's pretty much the same technique that we used in the previous set of notes in order to sketch polynomial graphs. We'll make just a couple of changes, and then I'm going to show you a shortcut that'll also help with sketching. First, though, let's look at a simple example. First, we always need the polynomial to be in factored form. That's easily enough accomplished. This one ACs nicely. This gives us our critical points of 8 and 3. Those are the zeros of the polynomial. Now we can draw the number line. We're going to have to decide whether or not to include the critical points in our solution, and so we need to plot this as either open or closed. To do that, we look to the original inequality. We're looking at greater than or equal to 0, and so the zeros are going to be included in the solutions. Now we can build our table for testing based on the factored form of the polynomial. We'll have 3 regions to test, and so here are the values I'm going to run through. Now I fill in positive and negative signs the same way we did last time. 2 minus 8 is negative, 2 minus 3 is negative. This will be a positive region. 4 minus 8 negative, 4 minus 3 positive. We'll have a negative region in the middle. Before we move on, I'd like to draw your attention to the fact that the signs are alternating across regions. This is part of the shortcut that I'm going to show you in a little bit. For now, though, let's continue. We're going to mark the regions where the sign matches the given inequality. In this case, our given inequality was greater than or equal to 0. That means we're looking for positive intervals. These become the regions that we highlight. Now that we have a proper map of the solution, we simply write that in interval notation. Recall that our directions told us to solve the inequality. That means we make a statement involving x. So, recall that interval notation is a form of set notation, and so the correct way to state this is x is a member of that set. We've seen this symbol before. That is a set membership operator. The symbol that looks like a C with a line through it is about halfway up the line, and it's small, about the size and location of a plus sign. This is our complete answer. The next example has a couple of differences from the last one. Most notably, we're using a less than sign instead of greater than, and we're using strictly less than. We're not including a solution where it equals 0. Try this example yourself using the same method from the previous page, and see if you can work out how to adapt the strategy to deal with this less than. Here's my solution. When we factor out an x, we're left with the difference of squares, and so we get 3 factors. Our critical points are the zeros, And so we have 0, 2, and negative 2. This gives us this number line. The fact that we're using strictly less than means two things. First, that the critical points will not be included. The critical points will be open because we're not including the zeros. Second, this also tells us that we're going to be looking for intervals that are negative. We are looking for less than 0. Here's my testing table. You should end up with a negative region, a positive region, a negative region, and a positive region. We're looking for negative intervals, so here's when we highlight the solution. And finally, we'll write that in interval notation. Once again, I'd like to point out that the intervals have alternating signs, minus, plus, minus, plus. This won't always be the case, but that's going to be part of our shortcut. Notice that the multiplicity of each factor is 1. That's part of it. Here's an example with multiplicities. Work this one out, and then we'll look at the shortcut. Here's my solution. Recall that a double root indicates a parabolic bounce if we're going to be sketching it. We're not, but it's a good way to help remember the shortcut when we see it. Now let's look back at the signs. So they alternate on either side of the 6, but they don't alternate on either side of the negative 1. It's no coincidence that negative 1 is the double root. If you think about a parabolic bounce, if we bounce off the axis, we will keep the same sign. We will either stay negative or we will stay positive. What that means is that all we need to do is test one region, and then we can infer the other signs by the multiplicities of the roots. I'll write out the shortcut at the top of the next example, and then you can try it out. Take a moment to digest this and copy it down, and then try the problem. Here's my solution. I'm going to make one change. Instead of saying critical points closed, I'm going to say zeros are closed. In a moment, we'll encounter some situations where we have critical points that are not zeros. We don't want them in this category. Now I simply test a very high x value, like 10,000. If I were to plug in 10,000, I would get something positive, and something positive, giving us a positive result. Now we find the adjacent intervals by looking at the multiplicity. Multiplicity 2 means we'll have the same sign. Same sign. Multiplicity 1 means we will switch signs. And we're done with that. Now we just fill in the solution regions and rewrite in interval notation. Notice that since the zeros are closed, we have one continuous solution interval from 1 all the way up. With this technique, we can also solve inequalities involving rational functions. This is like a fraction, except with polynomials. We can get critical points from the numerator or the denominator. We'll get them all. With one major difference, the denominator's critical points are not going to be zeros. They're always going to be open, because if we were to plug in, let's say -1 in example 5, we would get -1 plus 1. We would be dividing by 0. We'd get something undefined instead of 0. Let's see how this plays out. First, the information we can glean from the inequality itself. The zeros will be included, so they will be closed points. And we'll be looking for negative intervals. Here are our critical points from the numerator and from the denominator. We'll still build a number line. And now, just to make sure that nothing slips through the cracks, we're going to label the zeros, or the 0 in this case, with a 0, and we're going to label any denominator factors that led to critical points with undefined. So the zeros are closed, and the undefined are always open. Next, we test a very high number. We can still use our shortcut. So 10,000 minus 2 is something positive. 10,000 plus 1 is something positive. We have positive over positive, which is going to be a positive number. The multiplicities are both 1, and so as we cross each critical point, we alternate. Now we mark the solution interval, which is the -1, and finally express our answer in interval notation. Try the next 2 examples on your own, and then I'll catch up and show my solution. If you haven't tried this one yet, please pause the video and give it a shot. Here's my solution. Notice that we have a closed point. That will be part of the solution, and we need to include it with our interval notation. Thanks for watching.